So last time we were talking about friction forces, and we mentioned that there's two types of friction forces. There's kinetic friction and there is static friction. Now, they both have their own coefficient of friction. For kinetic friction, we have the coefficient of kinetic friction, which is mu sub k, and for static friction, we have the coefficient of static friction, which is mu sub s. Now, they both show up in their own equations in their own respective ways, but there's a materials property that we can generally find, and that's that generally, for any given material, mu sub s is greater than mu sub k. So any given material is going to have both a coefficient of static friction and a coefficient of kinetic friction based off of, material properties. And it generally is the case that the coefficient of kinetic friction is lower. And that should kind of agree with your intuition. Generally, it's easier to keep an object sliding than it is to start that object sliding. That probably agrees with your intuition. So is that pronounced like, no, it's mu. 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 Or I don't know, however you want to pronounce it. Mu like the Pokemon, right? Right, so that's just generally true. It's not always true, but it's a good rough starting point to start from. Right, so there's one more force to go over, and that is the elastic force. So the elastic force is a combination of tension and contact. It both pushes on things, like a contact force, and it pulls on things, like a tension force. So the easiest example of an elastic force is just found in metal springs. So metal springs and all elastic forces in general have produce what's called a restoring force. And what that means when we call a force restoring is it means that if there is a deviation from equilibrium, from an equilibrium state, then the force will come to push it back to equilibrium. Force, oops, that's not on the line. Force acts to return to equilibrium. And hopefully that, I know I'm using a word equilibrium, which you haven't necessarily defined before, but the idea is simple. It's right, like if you have a spring attached to a wall, and maybe you glue a block to it, if the spring's natural length, I'm putting that in air quotes by the way, is say somewhere out here, then there would be a force, let's call this the equilibrium position of the spring, then there would be a force pushing it back towards equilibrium. And similarly, that would be a spring force. If the spring is stretched so that it's further away from equilibrium, then there would be a force pushing it back towards equilibrium again. There is some place where the force is zero. And if the object moves away from that place, the object that's experiencing the force, then the force will point in a direction going back to that equilibrium place. So we can actually describe the force that springs, or that rather ideal springs produce mathematically. So let's say that this distance here, the distance between the object and the equilibrium position, let's call that delta x. Right? It's just a length. So in the 1600s, I think it was the 1600s, it may have been the early 1700s, an Englishman who's, by the way, a very mean hook, about the magnitude of a spring force of an elastic force is equal to K. Oh, am I?
Sam, it's cutting out a lot.
Am I still cutting out? Long gone? Okay. Well, this isn't good. I think I keep going because it'll be recorded, And if I come back, then great. I think that that's the right move because it'll be recorded correctly regardless. So Hooke's law is just a statement about can I call into the meeting? I don't. You mean like from a phone? I mean, how would I write? Yeah, I mean, but the issue is like it would be. I don't even have Zoom on my phone. Yeah, I can try. Let me try connecting, but it'll be bad audio. So, well, that's a good idea. I can just call the number. You're right. That's a good point. It's the same internet. Today just might be bad. Where is the phone number? Phone number, one tap mobile. Okay. Dialed by your location. I've never actually had to do this. What are callers? Okay. All right. Well, I'm just gonna try dialing and see what happens. See what happens. Come on, mouse. 963 9197 9960. Can you guys hear me?
Yeah.
Can Can you hear me? Oh, I can hear myself. That's really just confusing. Okay. I'm going to mute my. I'm going to turn off my audio on my PC. Okay, there we go. Excellent, excellent, excellent. I'm going to put myself on the phone. Hopefully, you guys can hear me now. Great. Okay, let's continue. So where were we? So we were talking about Hooke's law. So Hooke came up with this equation. Yeah. Hooke empirically derived this equation that basically said that the amount of force that an object experiences due to the elastic force is proportional to the distance that it is away from equilibrium. And that proportionality constant, it's just some number k that depends on the material properties of the spring itself. So this value k, it's called the spring constant. For perhaps obvious reasons, it is called the spring constant, and it has units, as most numbers do, and the units are newtons per meter, as expected. You multiply something with newtons per meter by something with meters, and you get newtons, which is exactly what we want. And this number basically encapsulates how stiff the spring is. So a larger K means that the spring is really stiff, i.e. if you stretch it a lot, you have a really big force. On the other hand, if it's not very stiff, if you stretch it a lot, you have a small force. So this is great. This is a formula that tells us about the magnitude of the force, but we can do even better. We can actually write a vector equation for Hooke's law, which basically doesn't just tell us about the magnitude, it also tells us about the direction of the force. And so we can write it out as the elastic force is equal to negative k times delta x with a vector. So now delta x really means it means let me put this down. This is x minus x equilibrium. So in this case, here we would have x equilibrium. X equilibrium might be this vector. And then the current vector would be this vector. And so x minus x equilibrium would be a vector that points this direction with some magnitude equal to delta x. And so stick a negative sign in front and you get the direction of the force, which points back towards equilibrium. And this will generally work. So this is a really useful equation. As long as you know what delta x means, and remember that these are like vectors from, or these are
this is effectively a displacement from equilibrium vector, then you're all set. Now you can just plug that in to whatever coordinate system you're using, and you'll be able to find the actual force vector of for a spring system. Now, if you're having trouble with that, and maybe the coordinate system is complicated, you can still just rely on the magnitude and then figure out the direction yourself. Yeah, so this elastic force is directed back towards equilibrium. That's always true. Right. I guess we do have one more force to talk about, but this one's real quick, just air resistance or drag. So air resistance and drag are the same thing. And basically, it's just friction, but in the air. Now, it's technically caused by a separate phenomenon, meaning that it's not actually a result of two things rubbing against each other, and it depends on different quantities, but it has the same dissipative effect, i.e. it acts to slow things down. The only difference here is there is no static. There is no static air resistance. And indeed, we can actually kind of quantify the properties of air resistance. Like what does the force that is, or what is the magnitude of the air resistance force dependent on? And that's not particularly hard. You could just do it by experimentally testing out different things, and you'd come up with these conclusions relatively quick. It is proportional to the cross-sectional area. So if you have a larger thing, then it will experience more air drag than something that is otherwise identical, but smaller. And that's because air resistance is basically a measure of how hard the air molecules are bouncing off the surface of your object. And if your object has a bigger surface, you have more air molecules bouncing off. So the larger surface area, the larger cross-sectional area, the more air drag you would expect. Also, it depends on the speed of the object relative to the air. And the reason for that is that if you're moving faster through the air, then the air molecules are bouncing off you harder. So they're going to impact you with more force. And then last point is that it depends on the density of the air. And again, if there's more air to bounce into, then you'll have more force. Now there's a bunch of examples, or rather 2 examples that I linked to at the end of the lecture, but may as well just continue on, or not at the end of the lecture. 2 examples that I linked to in the lecture notes. So those are all the different forces that we're going to run into. Occasionally we'll run into a new one, but when we do, we'll make sure to talk about it before I just throw you to the wolves. So now we can actually just start using these forces and work on problem solving. So what we're going to do, or rather what I would like to do, is spend a bit of time just going over, at least quickly going over, some types of problems you might run into and how I might solve them. So there's not going to be any new physics here. This is just how you would solve problems that involve forces and accelerations and Newton's laws and so on. So let's look at, sometimes you will run into problems that involve pulleys. Is they're going to be super common? The air resistance formula is no. So air resistance, the formula for air resistance is non-obvious. It's like not very easy to derive, and there is no universal formula. So that's why I didn't give you one. You can approximate it, but we're not going to worry about that. If you ever do need to worry about approximating it, I will give you the relationship. So we already know that pulleys let us change the direction of a tension force kind of for free, right? Because assuming the pulley is massless and frictionless, assuming the rope is massless, then the tension force just goes around. The tension force can just go around a pulley, and the tension force is still the same in magnitude, it just changes directions. So pulleys are good for turning tension forces, for redirecting them into some other direction that you can use for some useful process. So a good example would be a system like this. So you have a rope attached to the ceiling. You have a pulley attached to the ceiling over here. And then you have a pulley that's hanging from the rope that's attached to a block. So this is a really classic example. So this is complicated, right? Because maybe this block has a different mass than this block. And so this pulley, the pulley on the left, isn't attached to anything. It's just hanging from the rope. And so you have to figure out how it might move or how it wouldn't move. And you have to figure out how that depends on the various forces and so on. So the question you might see here is, if neither block falls, how do the masses compare? So let's try to answer that question. So the first thing we're going to do is we're going to draw free body diagrams. Now that's generally going to be, it's almost your first step, and I will outline a set of steps that you should use at the end of this segment. So let's do some free body diagrams. So we're going to do a free body diagram for the two things that are moving. By the way, we know that if the leftmost pulley moves, then so will the leftmost block. So let's do a free body diagram for the leftmost pulley, and let's do a free body diagram for the rightmost block, right? For those two things. We could have done a free body diagram for that, for both blocks, but it's not quite obvious how regardless, we will need to see the free body diagram of the leftmost pulley because the pulley could move, right? So here's the free body diagram for the pulley. I'm just going to draw it, but you could just treat it as a point. So we have a force pulling down on it due to, it's technically a tension force. Actually, we'll need a free body diagram for all three of them. So let's do free body diagrams for all three of them. So we have our pulley with a tension force pulling down on it. Let's call this tension of mass 1. It's the tension force that is coming from the block with mass 1, right? Actually, we'll just call that tension 1. And then there's two forces pulling up on it. Now, there's two forces pulling up on it from tension. And the reason why there's two forces is because imagine instead that you were just holding the weight. You were just grabbing either end of the rope, right? You were just grabbing it here and here. You would feel a force on both sides. And so for Newton's third law, you are exerting a force on the pulley on both sides. And again, we would observe that the forces would be equal and opposite. So or not equal and opposite. The force here should be the same as the force here. I.e., if you were to just hold these pulleys, like grab them with your hands, you would feel the same force on the left side as you would on the right side. And that's why the force pulling up on the pulley is the same for both ropes. Another way to see this, by the way, is that the rope is gripping on both sides. It's gripping the pulley on both sides and pushing it up. So there's going to be a force on both sides, and the amount that it's pulling up by is going to be a tension force. It would be exactly the same as if you had just glued ropes to both sides. Now, the reason the forces are the same and the reason they have to be the same is because it's a rope. Ropes always exert the same amount of tension throughout the entire rope. That's part of what makes a rope useful, because the tension force is constant throughout. So anytime a single rope exerts a tension force, it will always be the same as the force that it exerts anywhere else along that rope. It might be in a different direction, as we're about to see, but it will still be the same magnitude. All right, so that's one free body diagram. Those are the only forces that are acting on the. No, it'd still just be so we're going to solve for t. It's some variable that we're going to solve for. I mean, you could have called it 2t if you wanted to, but if there was just one, like coming out the top, then it would just be one force, right? The point is just that there's two forces, but they're the same in magnitude because it's coming off on both sides. Now let's do the free body diagram for the block. So for the block, the first block, M1, there's a force of gravity downwards. And there's also a tension force upwards. Now, that tension force is the same tension force that the pulley feels, right? Because that's what ropes do. They transmit tension force. They transmit equal and opposite forces across the rope. So this is basically the same as if the tension force caused by the rope pulling up on the block is equal and opposite the tension force pulling down on the pulley. Those have to be equal and opposite from effectively Newton's third law and the fact that the rope is massless. Now we have one more diagram to do, and that's for the second block with mass M2. There's going to be a gravitational force downwards, and there would also be a tension force upwards, pulling it up, right? Because it's attached to a rope up top, exerting a force, keeping it up. Now, what is the magnitude of that tension force? Well, it's part of the same rope as the rest, as this part, right? And we already called the magnitude of the tension force of that rope T. So this has to be also that tension force also has to be magnitude T. So now we have 3 free body diagrams, and now we just have to start doing stuff, start calculating, start doing algebra. There is no contact force here. So we could do a diagram for the second pulley, but the second pulley is not going to move regardless. It's attached to it's directly attached to the ceiling. Regardless of what the mass of the 2 blocks are, that pulley is not moving at all. The first pulley could move because it's not attached to the ceiling, and the blocks could move, but the second pulley is not moving. All right, so now we just have to apply Newton's laws to try to solve the system. And so we're trying to find a relationship between the masses of the blocks. So let's just do algebra until we get an answer. Yeah, so we're assuming that the whole system is not moving. Also, we're assuming that the pulleys are massless. It's a general assumption that we make. So if we know that the acceleration, oh, by the way, we should probably choose a coordinate system. So let's just choose for all of them. Let's just choose plus y is up. Just makes it easy. And there's no horizontal movement, so we don't have to worry about that. So the acceleration upwards for the mass is 0, which means that Newton's second law for that block is we get that T1, because that's in the up direction, minus FG1, because that's in the down direction, should be equal to m times 0. Should be equal to 0, right? That just tells us that T1 is equal to FG1. And we know what FG1 is. FG1 is just M1G, right? So this is just M1G because that's just the force of gravity. So that's one equation, super helpful. We also know that the first pulley isn't moving because the block isn't moving. Nothing's moving here. So we have that the acceleration here is 0, which means that the net force is 0 in the y direction. I should have written that here, by the way. If the acceleration is 0, then the net force in the y direction. If the acceleration in the y direction is 0, then the net force in the y direction is 0. That's from Newton's law. And so we can write what the net force is. In this case, it's 2 times T because there's 2 tension forces pulling upwards with equal magnitude, minus T1 equals 0. But we know what T1 is. T1 is M1G. So what we really have is we have 2T equals M1G, or put another way, we have that T is equal to M1G over 2, which kind of makes sense. Each half of the rope on either side supports half of the weight of the block that it's holding up. Your intuition should be fine there. Last step, or last equation to use, we know that the acceleration of this block is also 0. So the net force in the y direction is 0. And so what we have is we have that T2 minus M2G is 0. M2G being the gravitational force in the second block. And we know that T is M1G from the previous equation. Yeah, we're assuming the pulley is massless. So what we have is we have M1G divided by 2 minus M2G equals 0. And so we can cancel off the G's, we can add to both sides, and we get that M1 is equal to 2 times M2. And in fact, that's the relationship that we wanted to find. We wanted to find how do the masses of the blocks compare? And so what we find is that in order for them to not move, you have to have that M1 is twice as heavy as M2, has twice as much mass. And the reason for that is because you're basically leveraging the fact that the rope goes around the pulley twice rather than just being attached once. And that's why when M2 goes down, M1 goes up, but it'll only go up half as much. So we'll come back to this example in a minute, or actually right now. But I want to talk about another concept that will which pulley is the middle. It's referring to this one. I want to touch on another concept that will come up when in these types of examples, and that is the idea of constraints. So constraints are kind of they are equations. They're mathematical equations, or actually, let me write this out in words for you. It is one or more relationships between quantities. I'm running out of space. Between quantities that describe the system excluding Newton's laws. So basically, it's a way of relating two quantities. Like, for example, we might want to relate the acceleration of one block to the acceleration of the other, but you couldn't figure that out from Newton's laws. That's just something that you kind of have to establish separately from Newton's laws. It's just a way of, it's just an additional relationship, an additional equation that you get from thinking about the system. One constraint, by the way, that we've run into already is the constraint that tells us about the magnitude of the static friction force. This is a constraint. It tells us that the maximum possible value that the static frictional force can be is equal to the coefficient of static friction times the normal force. That's an example of constraint, because this is in this case, it's an inequality, but it's an equation that doesn't come from Newton's laws, but still influences the system itself. It still describes the relationship between two quantities in the system. So this would be a good example of a constraint. Now let's go back to the example we were just talking about. Drawing it again. Sorry, it's a rough drawing, but you guys know what I'm trying to draw anyway. So here's a question. If the second block falls 10 centimeters, how far up does the first block raise? So this is not, you can't answer this question just by applying Newton's laws. This is something that's separate. And hopefully your intuition is on point. But the trick here is think about what happens if M1 goes up, let's say M1 goes up 10 centimeters. How far would M2 drop? Well, if M1 goes up 10 centimeters, that means that there's 10 centimeters less of rope on both sides of the pulley, right? And that rope doesn't just vanish, and it can only go one place. It can only go towards extending the rope on the free side. And so if, for example, the left pulley goes up 10 centimeters, the right pulley has to go down 20 centimeters. And that's because that rope has to go somewhere. So in fact, we find that if the rightmost block falls 10 centimeters, then the leftmost block will raise 5 centimeters. So this is a question that you could have thought about. It has nothing to do with Newton's laws, but in fact, it implies a constraint on the accelerations of the two blocks. In particular, let's say that the left block goes up 5 centimeters in 1 second. The right block will go down 10 centimeters in 1 second, right? So this not only tells us that the changes in height are different by a factor of 2, it tells us that the speeds differ by a factor of 2. i.e., it tells us that that v1, the absolute value of v1 I'll just write the vector. v1 should be equal to twice. Sorry, v1 is 1/2 v2. So if v2, if the second block is falling at 10 centimeters per second, that means in 1 second it will fall 10 centimeters. So in the same second, the left block will raise 5 centimeters. Hence, we have a relationship between the velocities. And because the velocities are related that way, the changes in velocities are also related that way. And so what we end up with is a statement about the accelerations are also related by a factor of 1/2. So this is a useful equation. And really, this can be rewritten as, say, a1 in the y direction is equal to minus 1/2 a2 in the y direction. The minus sign just means that when one accelerates upwards, the other one accelerates downwards, and so on. And I've just captured that with a minus sign, and I've captured the direction with the y component. So this equation here is a constraint. This is an equation that you would need to come up with separately from Newton's laws in order to solve a problem. For example, if you wanted to solve the problem that was like, I don't know, one mass is 2 kilograms and the other is 10 kilograms. What is the acceleration of the masses? Like, what is the acceleration of mass 1? What is the acceleration of mass 2? You would have to use this constraint to solve that problem. Without it, you just don't have enough information. So, oh God, we're already pushing the end of lecture. Geez, we're probably going to go a little bit over. So another common example that we'll run into is the inclined plane. So the inclined plane, it's a simple machine, and you guys have all seen this in like a high school physics class. And basically, it's just a way of making problems harder. Sorry, but that's what it boils down to. So for example, imagine that you had a wedge in inclined plane, maybe with some angle theta here. And you have a pulley attached to the top and a block. Block is attached to a rope, rope goes around, attached to another block. This is maybe this has capital M mass, this has lowercase m mass. You might ask the question, if neither block moves, i.e. if they're sitting still, what is the minimum value of capital M? Now, let's think about this for just a moment. Let's say that capital M had like 0 mass. Then clearly the block would just fall, right? On the other hand, if capital M was super heavy, then the other block would just raise up. So there is some range. So assuming that there's no friction, there is only one value of M, of capital M, where everything's stationary. But now assume that there is friction. Well, that means that it takes a little bit of extra force to get it moving in either direction. And so if the block starts moving up, well, that would mean that the mass of capital M is large. And that means that it's overcome the frictional force to start sliding down. On the other hand, if the mass is too small, the mass of capital M is too small, then little m will want to fall downwards. And the only way that it starts moving is if it has too little friction or too little mass for the frictional force to counteract the tension force, and it would start sliding up. So in the case where where you have a minimum value of capital M, that means that if you made it just a little bit smaller, the block would start falling down. And that implies that the tension force has to be, sorry, not the tension force, the friction force has to be downwards, static frictional force. Yeah, so the tension force is helping it move, and the static frictional force is hurting it in this case. And there's also gravity that's hurting it too. So the way that we would handle this problem, and let's assume that this inclined plane has coefficient of static friction mu sub s. It's just a number. I don't want to tell you what the number is, but it's just a number that you can plug in. So the way that we would handle this is we would do much the same as we did before. We would start with force diagrams, write out the components of the accelerations, and then we would just apply Newton's laws. Here, though, it gets a little bit trickier. So let's do a force diagram for the big block M. So we have a block M, and it's at an angle. So the gravitational force is still straight down. But now the tension force is up and to the right. The static frictional force is down and to the left. And the reason it has to be down and to the left is because we're assuming that M is going to be, if M were any smaller, then it would move to the right. So the static friction force keeps it in place. And then we have a normal force. Now, this is the first time you've seen this, but the normal force is always perpendicular to the surface. So in this case, the normal force points up and to the left a little bit. So there's multiple ways that we could solve this, or that we could handle this, but the easiest way to handle this is to just choose a good coordinate system. So a good coordinate system would be a coordinate system that's tilted. So you have plus x over here and plus y over there. Now that's not the standard coordinate system, so you have to do a little bit of geometry. In particular, you would have to figure out the components of the gravitational force in that coordinate system using some trig. So this angle here is theta. This angle is also theta. So we can use that to solve our problem. Right, so let's figure out the components of acceleration. Already, we want that neither block moves, which means that the acceleration should be 0. But let's just call it a sub x and a sub y first. So in this case, a sub x, from Newton's second law, a sub x is just the net force in the x direction over m over capital M. And A sub y would be the net force in the y direction, also over capital M. This is just for the block with mass capital M here. So now we have to do some geometry. So let's figure out what is the net force in the x direction. Well, the x direction means this way, right? And so there's going to be a component of gravity that helps, that points in the negative x direction. T points in the positive x direction. It points along that angle. The friction force points in the opposite direction. And then gravity, well, we have to do a little bit of trig here. So we have F sub g as the hypotenuse. We have F sub g in the y direction as one of the legs, and then F sub g in the x direction as the other leg. So we can use some geometry, and we find that that is, oh no, I should call that F sub g capital M. It's fine. Yeah, that's fine. Call it GM. There we go. GMY and GMX, because there's going to be two forces of gravity. There's going to be one for the other block as well. So using, opposite sine of opposite over hypotenuse or whatever, we can solve for the x component, which is in the negative x direction of the force, in terms of the magnitude of the gravitational force pointing downwards. So this is equal to, so that component is minus FGM sine of theta. And we know that is the net force in the x direction. Similarly, the net force in the y direction, it's a little bit easier. You only have the normal force pointing up. And then again, we have a gravitational force pointing down, and it has this component, the other component of the triangle. So that would be FGM cosine of theta. Now we know that both of these are equal to 0 because the accelerations are equal to 0. So we have a set of equations that are going to help us. There's one set of equations. Now we have another object. By the way, it's usually a good idea to just put boxes around your equations so you can keep things straight. We have another object, the second block. So here, we have a block with mass lowercase m, and I'm just going to choose a standard coordinate system. You don't always have to choose the same coordinate system for the two separate, for different objects. And in fact, doing so in this case would have made it harder. So here we have a tension force pulling it upwards and a gravitational force pulling it downwards. Gravitational force is G sub or G little m. So again, if the acceleration is 0, AX is 0, AY is 0, then we know that the net force in both those directions are 0. So in particular, F net Y has to be 0 from Newton's second law, which implies that T minus FG little m equals 0. So there's our third equation. All right. Now, we're not done yet. We still have to implement a constraint. So as is, there are what? How many variables do we have? We have the masses are variables, mass 1, mass 2. We have tension, we have friction, we have normal force. That's five variables and only 3 equations. We would like to find we're not going to be able to get all 5 equations, but we will be able to get 4 equations to at least relate one of them to 0. Yeah, F net should be 0, but that doesn't help us because there's no forces in the x direction. That will just give us 0 equals 0, which is not useful. So we're going to implement our constraint. We know what the maximum value of the frictional force is. We know that the static frictional force has magnitude less than or equal to mu sub s times n. And so we can actually use this first equation. We can rearrange that first equation. Call this 4. Using equation 1, we have that T minus, I'm just going to write capital Mg now for the gravitational force, sine of theta, is equal to F sub s. And so what we can do now is we know F sub s is less than or equal to mu sub s times n. So that gives us that T minus Mg sine theta is less than or equal to mu sub s times n. And now you can see that there is going to be a maximum value of m, right? So if m, or a minimum value of m, because you're subtracting off something that's small, and so it'll have, and it's bound, and that thing is bounded above. It'll become clear after I do a little bit more algebra. So our equations now look like we have this equation, and then we have 2 and 3. So those are the equations that we have to work with. So we can establish from 3, I know I want to finish this problem and then we'll call it a day. So from 3, we have that the tension force is equal to little m times g. That one's pretty easy, right? And from 2, we can solve for n. So it's n minus capital mg cosine theta. So n is equal to capital mg cosine theta. And so we can just plug those into our, plug both of these in here. So we have little mg minus capital mg sine theta is less than or equal to mu sub s capital mg cosine of theta. So let's cancel out the g's. Let's isolate little m just to make it easy. So we have m is less than or equal to capital M sine theta plus mu sub s capital M cosine of theta. And then we can factor m is less than or equal to capital M sine theta plus mu sub s cosine theta. And then we can solve. So we get that m divided by sine theta plus mu sub s cosine theta has to be less than or equal to capital M. So this gives us the minimum possible value of m. If capital M is any smaller than this thing, then it'll slide. So here we use, like, this is an involved problem. It's a hard problem. So, don't fret if you didn't follow. But all we did is we had to make an initial assumption about what direction the frictional force has to go. To do that, we kind of had to understand what was happening in the problem, i.e. what does minimum value imply? Minimum value of the mass imply? It implies that it would scoot upwards if there were no frictional force. And then we just hit this with a lot of algebra and a lot of Newton's laws. We implemented our constraint, which is indeed a constraint, and then that yielded our inequality, which tells us that m has to be bigger than a certain value, otherwise it will start to slide. Now, we did not get nearly as far as I would have liked to today, which really is a bummer. Fortunately, the next thing, actually, you know what I'm going to do? I'm just going to write down a summary of the steps I just did, and then we'll call it there, just so you guys can see that. So just a quick summary, just a few steps long. First step, draw a diagram, like I did. Second step, isolate the relevant objects. And draw their force diagrams, or free body diagrams. Step 3, choose convenient coordinate systems. They don't always have to be the same, but you do have to choose a coordinate system. And generally, it's a good idea to actually draw a picture of what your coordinate system is, just to keep it straight. So you do it for each free body diagram. Step 4, decompose the forces into components. We need to find the x component and the y component of each force. That way, then we can then add them up and find the net force in each direction. Step 5, we find, after using that decomposition of forces, find the net force in the x direction and the net force in the y direction, and apply Newton's second law. Step 6, apply any constraints. That means write down an equation and then perhaps use them. Maybe do some substitution if you can. And then step 6 is solve the algebra. And that's it. 7 steps, you can solve any free body diagram problem. All right, so I know I ran over, sorry about that. I'm gonna stop recording here